In 1948, Union Pacific encountered an insurmountable challenge for conventional locomotives. A surging volume of freight meant even their robust big boys proved too costly, and diesel configurations faltered on Wyoming's Sherman Hill. The executive board then mandated a locomotive with the strength of an armored warship. Their solution was a jet turbine engine, so thunderous it rattled homes, yet so mighty it shattered all prior freight records. However, if this machine represented the future, its swift disappearance begs an explanation. Music. To grasp this, one must first comprehend the critical nature of the mission before anyone dared to construct the world's most cacophonous music train. Sherman Hill was the ultimate bane for railroads. Music. It manifested as 7 miles of Wyoming granite. Between Cheyenne and Beaufort, the track ascended a 1.55% westbound incline, a seemingly modest figure, until one is attempting to haul 5,000 tons of freight music behind them. This was no gentle slope. For decades, it stood as the most precipitous segment of Union Pacific's main line, a stretch where steam engines consumed prodigious amounts of coal and taxed human endurance just to maintain momentum. By 1948, the conflict had ended, but the struggle with the hill was merely commencing. The post-war economic boom caused freight volumes to surge by 50% in a single year. Daily, dispatchers witnessed yards overflowing with boxcars, tankers, and hoppers, all awaiting their turn to struggle up the grade. The big boy steam locomotives could conquer it, but at a severe cost. Mountains of coal, incessant music maintenance, and crews toiling relentlessly. Diesel power was envisioned as the future. Yet, on Sherman Hill, the reality presented a logistical quagmire. A single EMD-F3 diesel generated only 1,500 horsepower. Music. To propel a heavy westbound train, the railroad had to couple 4, 5, or sometimes even 6 units together. This entailed fueling 6 engines, inspecting 6 sets of wheels, and facing 6 opportunities for failure. Should one unit stall or lose power, the entire train could be marooned halfway up the ascent. Delays mounted. Music dispatchers reorganized schedules and hoped for clear tracks, but the bottleneck remained formidable. Operating personnel termed it a squeeze. The railroad required more trains, but the hill imposed a strict limitation. The horsepower deficit was undeniable and increasing. Union Pacific faced a dilemma: continue assembling disparate engines, or discover a single machine powerful enough to conquer the hill permanently. In 1948, Union Pacific's boardroom was not a place for half-hearted measures. The financial records were stark. Operating a single big boy steam locomotive over Sherman Hill incurred annual costs exceeding $500,000 in coal, water, and labor. Crews worked continuous shifts just to keep the behemoths moving, while maintenance yards were overwhelmed with worn parts. The new diesels, Music, promised cost reductions, but the reality proved even more expensive. Every heavy train necessitated a procession of engines and crews, and every malfunction amplified the expense. The railroad's senior leadership, spearheaded by Otto Kuhler and President William Jeffers, confronted a critical decision. They could persist in consolidating fleets of underpowered diesels, or they could venture into the unknown. The board's directive was unequivocal. Cease thinking small. Find a singular locomotive possessing sufficient might to ascend Sherman Hill autonomously. A machine wielding the power of an entire fleet. meeting minutes from that year captured the urgency. Freight was accumulating, and every delay jeopardized Union Pacific's standing. The demand for a solution was intense. As one executive articulated, they needed a battleship on rails, not a flotilla of rowboats. The financial disparity was undeniable. Steam engines depleted the budget, but combining 5 or 6 diesels was only marginally better. The true breakthrough would originate from something revolutionary: a locomotive capable of replacing 5 diesels, operating longer between overhauls, and eradicating the bottleneck once and for all. By 1948, Union Pacific's mandate was unambiguous: construct the most powerful locomotive the world had ever witnessed. Whatever the cost, Vincent Mertz, a General Electric engineer, observed a jet engine and perceived more than mere flight. He saw the resolution to a railroad's formidable challenge. While most within the industry dismissed turbines as impractical for rail use, Mertz and his team were oriented towards revolutions per minute, not adherence to tradition. The query was straightforward. If a turbine could propel a fighter jet through the sky, why couldn't it toot a freight train over the Rockies? Aviation had already demonstrated the raw power of turbines. In the skies above Korea, the F-86 Sabre and MiG-15 were redefining the parameters of speed and force. The fundamental principle lay in the cycle. Air was drawn into the compressor, intensely compressed, mixed with fuel, and then ignited in a controlled explosion. This force rotated a turbine wheel at speeds reaching 6,900 RPM so rapidly that engineers had to develop novel alloys to prevent the blades from disintegrating. The exhaust, screaming out at 800 degrees Fahrenheit, was hot enough to strip paint and warp steel. Yet, the innovation was not solely in the heat or speed. It resided in its simplicity. A turbine possessed a mere fraction of the moving components of a diesel engine. No pistons reciprocating back and forth. Music. No crankshafts twisting under strain. Just pure, continuous music rotation. With each revolution, the turbine delivered smooth, unwavering power. Mertz's notes from the late 1940s stated it plainly. Aviation power adapted for rails equals 10 times the horsepower per pound. The challenge lay in transferring that airborne energy to steel rails. Aircraft turbines were engineered for high-velocity flight at 30,000 feet, not for laboriously climbing a mountain with a mile-long train in tow. Music turbines performed optimally under sustained, heavy loads. They did not favor idling or throttling back. Nevertheless, the figures were compelling. A single gas turbine could produce 8,500 horsepower, surpassing by more than 5-fold the output a standard diesel could generate. Music. The prospect of replacing an entire string of diesels with one machine was sufficient to make even the most skeptical railroad executive music reconsider. Skeptics within the industry highlighted every conceivable reason for the concept's failure. Turbines rotated so rapidly that any defect could lead to catastrophic breakdown. The exhaust was so intensely hot it threatened to scorch tunnels and bridges, and the sound, engineers quipped, was akin to standing behind a jet during takeoff, only magnified. But Mertz remained undeterred. He was convinced that with meticulous engineering, the brute force of turbines could be adapted for rail applications. General Electric's initial test facilities in Schenectady became a proving ground. Engineers operated turbines at full capacity. measuring vibrations, evaluating alloys, and determining the maximum quantity of air and fuel that could be propelled through the system before failure occurred. They designed intake screens to guard against birds and debris, and constructed robust generators to convert all that rotational energy into electricity for the traction motors. Each test pushed boundaries, and every success brought the concept closer to fruition. Union Pacific's leadership observed with increasing intrigue. The conventional approaches, assemblies of diesels, legions of steam crews, music, were nearing their limit. The turbine presented a blank slate. It was a calculated risk, but the stakes, music, were evident. Conquering Sherman Hill would enable the railroad to transport more freight, more swiftly and at reduced cost. Mertz's vision, conceived in the jet age, was poised to confront the granite of Wyoming directly. The transition from sky to rail was no longer a mere fantasy. It was a blueprint ready for construction. In 1958, Union Pacific received a machine that resembled a mobile industrial experiment, more than a traditional locomotive. The railroad dubbed it the Big Blow. It comprised 3 distinct units, extending almost 200 feet from front to rear. At the forefront sat the cab, a fortified structure of steel and glass where the crew commanded the train high above the tracks. Behind it resided the turbine car, a colossal steel enclosure housing the engine's core, a gas turbine spinning at 6,900 revolutions per minute. At the very end was a fuel tender, reminiscent of a diminutive oil tank on wheels, its walls lined with heating coils and insulation. Union Pacific's procurement team had one uncompromising demand: unadulterated power. General Electric responded with a turbine capable of producing 8,500 horsepower, eclipsing the output of any diesel music locomotive then available. The Big Blow didn't merely overpower its rivals, it redefined the possibilities of what a locomotive could be. The turbine car alone, fully fueled, weighed over 200 tons. The generator inside was so immense it had to be crane-lifted into place at the factory. When the turbine ignited, the sound was more akin to a jet engine than a train, a high-pitched whine audible for miles. However, the true brilliance wasn't solely in the horsepower, it was in the fuel. Instead of consuming costly diesel, the Big Blow ran on bunker C, a thick, tar-like residue remaining at the bottom of the oil barrel. In the 1950s, bunker C was so inexpensive that refineries practically gave it away. Most railroads wouldn't consider it. It was too impure, too viscous, and too problematic. But Union Pacific recognized an opportunity. The tender was equipped with electric heating coils that maintained the fuel at 250 degrees Fahrenheit, just hot enough to transform the sludge into a liquid. From there, it was pumped into the turbine's combustion chamber, atomized, and ignited in a roar of blue flame. This was an economic innovation on an industrial scale. At merely music and 3 cents a gallon, bunker C cost a fraction of diesel. The Big Blow could operate for hundreds of miles between stops, consuming a fuel no one else desired. The tender had a 24,000-gallon capacity, leading to fewer refueling stops and more music time dedicated to freight transport. Every component was engineered for durability and efficiency. The turbine itself contained only a handful of moving parts compared to the thousands within a diesel engine. Fewer moving parts translated to fewer breakdowns and less time in the repair shop. Inside the cab, engineers encountered a control panel unlike anything they had operated before. Instead of accelerating a diesel engine, they managed a jet engine, monitoring its temperatures, fuel flow, and turbine speed. The startup ritual involved priming the lines, heating the fuel, bringing the turbine to idle, and then unleashing 8,500 horsepower with a twist of the throttle. The immediate benefit was clear. A single big blow could propel 100 loaded boxcars up Sherman Hill at speeds that dwarfed the performance of conventional engines. Union Pacific's decision to embrace this design was based on precise calculations and simple economics. Every mile the big blow covered on inexpensive fuel resulted in savings. Every train it pulled, eliminating the need for helper engines or multiple diesels, reduced labor and maintenance expenses. By 1958, the railroad owned a machine capable of performing the work of 5 diesels for a fraction of the fuel cost. The big blow was more than just a new locomotive. It was a declaration. For a brief period, Union Pacific transformed the railroad's biggest challenge into a showcase of American engineering prowess. The first time a big blow left the yard at full throttle, every head in Cheyenne turned. The sheer volume was enough to shake windows and cause dogs to bark for miles. For the crews in command, it was an entirely different experience. Engineer Bill Price recalled the turbine's shriek as comparable to 10 747s spooling up simultaneously. A vibration so intense it made the cab tremble and his teeth hum. Fireman Ray Delacote quipped that the air intake could have snatched the hat right off his head if he ventured too close. However, once the throttle opened and the train began to move, all anyone could do was hold on. On Sherman Hill, where steam giants had labored and diesels had struggled, the big blow tackled the grade effortlessly. One engine 3 units long pulled 100 loaded boxcars up, a 1.55% grade at 40 miles per hour. The figures were astounding. Each turbine averaged over 100,000 miles annually, operating almost continuously from Council Bluffs to Ogden and back. Despite comprising less than 2% of Union Pacific's locomotive fleet, these machines transported more than 10% of all the railroad's freight. This is not an exaggeration. 1 out of every 10 tons traversing the Rockies was hauled by a turbine. The power was often so overwhelming that it occasionally exceeded the capacity of the equipment it was designed to protect. There's a tale from 1960. A big blow with 100 cars began its ascent of Sherman Hill, a bit too aggressively. The coupler on the lead car snapped with a loud crack, sending the rest of the train rolling backward down the grade. This was not an isolated incident. If the engineer was careless with the throttle, the turbine could literally tear steel couplers in two. The operational rules had to be revised to accommodate this immense force. Crews described the experience as both terrifying and exhilarating. The cab vibrated constantly. The heat from the turbine could blister paint 50 feet away. And the noise was so intense that personnel wore earplugs just to get through a shift. But when the train reached the summit at speed, without assistance and without delays, it felt like a triumph. For 2 decades, the big blow not only met the challenge of Sherman Hill, but conquered it. The critics who labeled it a monstrosity had to concede that this monster could move mountains. The existence of the big blow was always precarious. Despite its immense power, the turbine possessed a fundamental flaw that no amount of engineering could conceal. The moment it operated below full throttle, the metrics turned unfavorable. Unlike a diesel, which could idle quietly and conserve fuel, the turbine consumed bunker C at nearly the same rate, whether stationary or hauling 100 cars up Sherman Hill. Crews dreaded prolonged waits at red signals or sidings, as every wasted minute meant gallons of fuel burned and dollars dissolving into the Wyoming winds. Union Pacific's accountants observed the escalating fuel expenditures. When the initial turbines debuted, Bunker C was refinery waste, thick, black, and almost worthless. At 3 cents a gallon, it was the loophole that made the entire venture feasible. However, by the mid-1960s, the global landscape shifted. Chemists discovered methods to convert heavy oil into plastics, triggering a new gold rush in the petrochemical sector. Suddenly, a substance no one desired became the raw material for everything, from toys to automotive components. The price of Bunker C didn't merely inch up, it skyrocketed. By 1969, it cost almost as much as diesel, nullifying the sole advantage that had kept the turbines profitable. The boardroom discussions grew more contentious. Internal memoranda from 1967 and 1968 articulated the stark reality. Turbine fuel costs had doubled in less than a decade. What once saved Union Pacific a fortune now jeopardized the financial viability of their most ambitious fleet. Economists within the company crunched the numbers and found that the break-even point had vanished. When maintenance and fuel costs were combined, each turbine cost nearly twice as much per mile as a modern diesel consist. Railroad President John Kennick stated it unequivocally. Continuing to operate the turbines would hemorrhage company funds. Noise complaints further amplified the pressure. The turbine's shriek, once a symbol of power, became a liability. As suburbs expanded along the tracks in towns like Rawlins and Cheyenne, residents filled council meetings with accounts of sleepless nights and shattered windows. While no formal bans were legislated, the message was unambiguous. Keep the monsters away from residential areas, or face a political battle. Union Pacific quietly began parking turbines in remote sidings, idling them far from city limits, which only exacerbated their inefficiency. By 1970, the conclusion was unavoidable. The turbines were retired from service, their colossal frames parked in dead lines. Most were scrapped by 1979, their engines silenced before the first oil crisis could even rewrite the global energy rules. For all their might, the big blows were outmaneuvered by the very forces that had initially made them possible. Economics, public pressure, and the relentless march of technology closed the chapter on America's loudest locomotive. Today, railroads prioritize efficiency and quiet operation. Nevertheless, the demand for raw, disruptive power never wanes. As global shipping requirements escalate and energy sources evolve, the question resurfaces. Will we dare to construct machines that challenge conventional limits, even if they don't conform to societal expectations? Progress is not always subdued. Sometimes it reverberates through the very ground beneath us. Let me know your thoughts. Will a novel turbine ever roar back to life?